Welcome to lecture number 2. Of all the lectures I'm going to give you, this very well may be the most important one. So it certainly is for the first half of the show, first half of the course. So try to get some coffee and pay attention on this one. So we're going to start off with a beam that is pre-stressed. But here's an important point. It is a weightless beam and has no applied loads, and that is extremely important. So what you're thinking as you're watching this is I've got a beam just like you had a beam in your statics class, and it looks like that, and it's got no loads on it, has no weight to it. This is the beam that we are analyzing this entire lecture. And I want you to remember that because it's going to get confusing. I promise you it's going to get confusing. I've been doing this for many, many years, and I'm going to do my best to bring everybody along. But this is the lecture that some people really struggle with. So we're a weightless beam, no loads, no applied loads. So that means no reactions, no shears, and no moments. And it means that everything in your statics class that you learned was true. We're not changing anything. But if you go along in your career, you're going to run into people that get confused about that. Will say crazy things like statics doesn't apply to pre-stressed concrete. Somehow pre-stressed concrete just doesn't follow the same rules. Well, that's not true. Statics is your best friend. It's your friend for life, and never forget it.
Back in, that's my best friend. She a rope that bitch, drive her own car. She don't need no lift in the
Okay. It's your best friend, so that'll help you remember. So statics still applies, and if you just leave the class with one concept, it will be that statics still applies to pre-stressed concrete. But let's take a hard look at it. And so why would that be such a confusing thing if we're all so sure about it? Well, in this case, we are pre-stressing to 120 kips. So we've got tendons in this beam that are stressed to 120 kips. So what does that mean? What does that do to the beam? Well, the first thing I want you to remember is it doesn't do anything to this beam. In fact, I ask the question a lot each year. And I say, when you were in statics and they gave you a beam and they gave you a beam with a load on it, was that beam ever a pre-stressed concrete beam? And people scratch their head and I don't really know. And the answer is that's a trick question because they never did tell you what type of beam that was in statics. Statics doesn't care. That's the point. Statics doesn't care if that's a bamboo stick or a steel beam or a wood, sawn lumber or glulam beam or a concrete beam. Statics is statics. So you may have had a pre-stressed concrete beam. Who knows? But it wasn't important to mention it. So here is one that's pre-stressed. So it still has no reactions, no shears, and no moments. But it's going to have some things going on. Let's start by taking a section right here and looking at the tension in the pre-stressing. So we cut a section, 120 kips must be in tension. Now, if there's no moment on this, there's got to be an equal and opposite compression. So the material, which will become concrete very shortly, but whatever this weightless material is, it is equally feeling compression. We can't have this tension without also feeling a compression in the beam itself. So that compression must be collinear with that tension force. If it wasn't, there would be a moment on it. And you're familiar when you have a compression force and a tension force, that TC couple, that tension and compression have to be equal to each other because of statics. And the distance between the two creates an arm, and that moment couple multiplied by that arm tells you what moment there must be at that location. If there is no moment, what I'm saying is that these must be collinear. So that's what we're starting with. Remember, a beam that has no load on it and no weight. Now, the first thing I want to talk to you about is what we do when we are going to be mainly interested in the concrete only diagram. That's where we're going with this, because the end game here is to calculate the stresses in the concrete. But we are going to start off by both looking at the tendon diagram, because it's extremely important, and the concrete diagram separated. So in this tendon diagram, there's a tension force on the tendon group of strands of 120 kips. The concrete, as we set up here, needs to be balancing that, and that actual centroid needs to be at the same location as the tension force. But we're going to do something. We are going to take it from where it exists, and we're going to move it up to here. In fact, we're always going to do that. We are always going to take the force wherever it exists on the concrete and place it at the center of gravity of the concrete. Now, that's not statically correct to do that, because we moved a force that was down here up. So we created a moment that's not there. We created a moment going that way by just moving that force up. So we have to counteract what we've done to make statics work and provide a counteracting moment equal to the moment, or equal to that moment is equal to the force times the eccentricity that we moved it. Okay. So, follow me please on this. We can have a beam with no external loads, no weight to it, but with stressed tendons. So if we only look at what's happening to the concrete is actually experiencing stress. It's experiencing that compression. It's also experiencing a lift. It's experiencing a moment in and of itself. So it will have a concrete-only moment diagram. That F times E is the primary pre-stress moment diagram. However, the tendon-only diagram, or the tendons themselves, are doing the exact opposite. These are self-resolving within the beam. So whatever is happening statically to the concrete, the opposite is happening to the tendons. Whatever the tendons are doing to the concrete is doing back to the tendons. They're self-resolving within this beam, and that's why in statics nothing is happening. There is no reaction, there's no static shear or static moment. But if we separate the pieces and components, the concrete on one hand and the tendon diagram on the other, well, then there seems to be some activity happening. But you put them together, because they are acting together, and there's nothing net happening. So whatever, if we're going to stress a tendon, put compression in the concrete by putting tension in the tendon, those things statically will offset each other. But you will still have stresses, and you can still have deflection. So this is where the confusion begins, and we keep going. It gets worse. So we can have a beam, statically nothing happening to it, but the concrete itself is under not only compression, but it's under some bending stress. The bending stress, that primary pre-stress moment divided by the section modulus to the top, will tell us what the stress is at the top, flexural stress. That primary pre-stress moment divided by the section modulus to the bottom will tell us what the bending stress component of that is at the bottom of the beam in the concrete itself. And then we'll subtract F over A. By the way, in this entire course, compressive stresses will be negative. So F over A will always have a negative sign in front of it. In this particular case, tension is being created on the top, and remember how we talked about last time, it's extremely important to know where tension is occurring. That tension on top will create a positive tensile stress at the top. So this is positive. So that's M over S will be positive. This M over S is creating compression. That M over S is negative. So we're trying to be consistent. Compressive stresses will be negative. Tensile stresses will be positive. Okay, so let's calculate that primary pre-stress moment diagram, and we'll draw it to the tension side. That primary pre-stress moment diagram at every point is the force times the eccentricity at any point. So the eccentricity here is 0, so that moment diagram will be 0. The eccentricity is 11 inches here, so that force of 120 kips times 11 inches divided by 12 is 110 foot kips at, this floats on me sometimes, at that location. So we can draw the primary pre-stress moment diagram right off the bat. All we need to know is what the force is in the tendons and where the tendon CGS is relative to the concrete CGC. That's what this diagram is. Very easy, and many people might think, well, that's all you need. Back in the 1960s, a guy named T.Y. Lin came up with something and said, well, that's great. We can take the force times the eccentricity and create a primary pre-stress moment diagram, create a pre-stressing moment diagram. But what if we were to create that moment diagram not by knowing where the tendon itself is and what the eccentricity at any location was? What if we came up with what we will call an equivalent load? This is an extremely important part of what we're doing, and I said this lecture is probably, quite possibly, the most important lecture that I'm giving you in the whole course. What is that equivalent point load? What does that mean? Why is it important, and why will it become so powerful? Well, if we can come up with a load that's not really a load, because remember, this beam has no applied loads on it. Very important. So this isn't an applied load. This is what we're going to call an equivalent load. And it's something that the tendon is doing to the concrete and the concrete is doing back to the tendon. So this point load will actually be going in two different directions. And in your first homework assignment, you're going to be drawing the tendon diagram and showing me all the equivalent loads holding the tendon in place. And then you're going to draw the concrete diagram, concrete only diagram, and show the exact opposite of all those equivalent loads acting on the concrete. Put them together and they cancel each other out. But this is what's important. What I'm trying to do here is show you that there is one and one load only that would create that moment diagram. Now, back when I was a young pup, I would just tell everybody it's only a point load. Only a point load could create this moment diagram. But over the years, there are people who want a little bit more than just my word for it. So I created the notes that you're looking at and that you have. And you can study these as much as you feel like, but this is my basic proof. I'm starting and working backwards from the moment diagram that we all agreed that we had, the force times the eccentricity. To create a linear moment diagram, calculus actually says that the moment diagram is the integral of the shear diagram. You remember that. So the area under the shear diagram creates the moment diagram. And the derivative of the moment diagram creates the shear diagram. So you can work in either direction. But if you have a linear moment diagram, you must, by taking the derivative of that, have a constant shear diagram. So if this line is linear, calculus told us that that must be constant. Okay? If this is constant, if this shear diagram is constant and it has a jump in it, the only way that that shear diagram can be generated is by a reaction, another force up, creating that, and another force down. You have no other choices. This is exactly what has to happen if you're starting with this moment diagram. And remember, we've agreed that the force times the eccentricity, the primary pre-stress moment diagram, is this diagram. So in general, we have a linear diagram, we have a constant shear diagram that can only be created by a point load. So the point in all of this is there is no other load that you can put on to get this same moment diagram. Has to be a point load. So we have a unique point load, equivalent point load that will create the primary pre-stressing moment diagram. Right now you're asking, well, why would you want to do that? It's so easy to just create it, multiplying the force times the eccentricity, but that's what we're here for, and that's what your first couple of homework assignments will show you. But when T.Y. Lin came up with this, it really revolutionized all of pre-stressed concrete. Knowing the force times the eccentricity is the primary pre-stress moment diagram gets confusing as soon as you actually try to apply it to some real type situation. Using another load to create the same effect makes life much easier for us. That's what we do as engineers. If somehow, some way, the pre-stressing can be depicted in our calculations as just another load, that's a game changer for us. Now it's just another load case. Now the dead load is the dead load case, the live load's the live load case, and the pre-stressing can be another load case. And we just mix and match and combine, load factor, do whatever it is that we need to do to design whatever it is we need to design. But the fact that the pre-stressing becomes another load case changed the world. And I don't think I'm being over dramatic. It certainly changed the pre-stressed concrete world. So we can, knowing that this was 110 foot kips, and knowing that that's a point load in the center, PL over 4 is equal to 110, and we can calculate that equivalent load, if there was a load of 11 kips, which there isn't, but if there was, it would create exactly that same moment diagram. Let's see how that can be useful to us. And again, we put that, just to prove what's somewhat obvious, we put that 11 kip point load on the beam. We get a concrete only shear diagram. And from that shear diagram, we're back to that original primary pre-stress moment diagram. Voila, magic. You're asking yourself, why do all this? Well, I'm hoping that becomes clear. The best way to make things clear to you young people is to have you do a homework assignment and prove it to yourself. So that's what we will do. Okay, starting with the moment diagram and working our way back and solving for that point load was one way to do it, and it's not the efficient way to do it, and it's not the way I actually even want you to do it. What we could have done is started back with just that 120 kip force and the slope of those tendons. So if I do that, and I just say there must be an equivalent load holding this tendon in place. And by the way, the best way to think about all of these equivalent loads, think about that tendon floating in space, not attached to concrete, just by itself, that it's taken on some shape and it's got some tension force in it. What does it take to keep it in that shape? Because any string, any cable will just try to straighten out if you pull on it. And that's the way to think of pre-stressed concrete, is that we stress these tendons and all they want to do is go straight. They just want to be straight between the two ends being pulled. Something's resisting that. Well, that's the material resisting that. The concrete will be resisting that. But if you think about it in terms of loads, this equivalent load is what is being applied to that tendon to keep it in exactly where it is. Think about it floating in space. So I can actually calculate that equivalent point load by just looking at the force in the tendons and the angle of the tendon. So this angle and this angle. Both of these are going up 11 inches. And in this particular case, they're doing it over the same length. So the vertical component of this 120 kip tension load in the tendons is 2 times 11 over 240. We'll use small angle theory. So 2 times 11 inches divided by 240 gives me that same 11 kips. A much easier way, and the way I want you to do this, from first finding out what the moment diagram is and then backing into the point load that must create it. This is the superior way. So no matter what I give you, you'll actually be able to look at the tendons, and wherever there is a discontinuity in the tendons, wherever it changes direction, there must be some type of equivalent load on there. Now, right now we're limiting that to point loads, but we're going to have other kind of loads. So that component of 11 kips, if we look at the tendon, which is what we just did, that equivalent point load is going down. The force that we applied in the tendons is going horizontally, and there must be a vertical component also holding this in place. I mean, think about pulling on this. If we're pulling on this, this wants to go down, and it's being held in place. So that's the way I like to think about this. If you want, just don't think about this dotted line of the beam. Just get rid of it in your mind and just have a floating tendon in space. If you want to hold it in space, there must be all of these forces applied to it. And then it's not going anywhere. Those are the loads on the tendon, and those loads actually must be being created by this weightless material or this weightless concrete. So that material, or that material is going to be concrete, as you probably figured out when you signed up for this course, is feeling the exact opposite, the exact equal and opposite. Combining these two, remember, combines to nothing. You will have some stresses in the tendon, of course, because we put them there. We stress the tendons. There will be stress in the concrete that we just talked about. There will be some bending stress and some compressive stress. But statically, nothing is happening, and that's a tough concept. That's the concept that people struggle with and start battling with their fundamental beliefs of statics and equilibrium. But remember, these two things are canceling each other. Now, I'd say the vast majority of the world thinks about pre-stressed concrete only in these terms, only in what the tendons are doing to the concrete. And most of them have never even considered the fact that the concrete is doing the exact equal and opposite to the tendons, and that these cancel out. So the concrete is feeling compression, and that's a great thing about pre-stressed concrete. We're compressing concrete. Concrete likes to be compressed. That closes up any cracking that wants to happen. It gives it a nice P over A compressive stress to start with. And we're going to need that. We're going to want that. And in most of pre-stressed concrete, and really all of post-tension concrete, we're also trying to lift the beam. We're also trying to counteract gravity or the loads that are being placed on the beam. That's the only time pre-stressed concrete makes sense, is if we are counteracting what gravity is doing. If we were doing it in the same direction, it probably wouldn't be nearly as successful. But we can counteract gravity. You have all of these notes, so I'm not going to go through every single part of it, but you can see and understand the concept. Same thing here in this example. I just moved the location over. It shouldn't be too confusing. We still have that same primary maximum pre-stress moment diagram, but at a different location. It's now 30 feet. That primary pre-stress moment diagram creates simultaneously a shear diagram. We could have calculated that by just looking at the components again of the pre-stressing force. So we'll take this, look at that same 120 kips. It's got that same eccentricity, but the slope of the tendons is now different. Each side is still going up 11 inches, but this is doing it over 360 inches, and this is doing it over 120 inches. The vertical component from this side is 120 kips times 11 over 360, or 3.67 kips. The equivalent load from this side, force in the tendons times the 11 over the 120, and we get 11 kips. This time, we sum the two of those together and actually get a greater load than we had last time. 14.67 kips is the equivalent load now holding that tendon in place. Just to prove to ourselves that the stuff is going to make sense, we put that 14.67 kips on at 30 feet, come up with that same shear diagram, and more importantly, come up with that same primary pre-stress or concrete only moment diagram. Okay, so that feeling good about how we handle equivalent point loads and straight or linear tendon profiles. What happens when we have a parabolic tendon profile? Well, we start with the same process. F times E at any location. E is varying, but it's varying parabolically now. So we have an F times E at any location. And remember, the maximum drape is A. E, there's an infinite number of them throughout the span of the beam. There's one A being the maximum. So it's really, in this particular example, A is the maximum value of E. Not always that way. Don't write that down. Just happens to be the way. So we start with that moment diagram, and again, we're going to work backwards just like we did before. We can work into the shear diagram that must be created by a parabolic moment diagram. Remember, the derivative of a parabolic moment diagram, a second order squared equation, is going to be a linear equation. So the shear diagram created by a parabolic moment diagram must look like this. Has no other choice. So the load required to create this shear diagram, again, you take the derivative of a linear shear diagram and you must get a constant force or a constant load. So I'm trying to prove to you using some simple calculus recollection. This moment diagram is the derivative or is the integral of that shear diagram, but we're working backwards. We're working the other way. So we're starting with a second order something x squared, coming back to a linear shear diagram, and a constant loading diagram. The important thing here is if we have a parabolic moment diagram, that had to have been created by a uniform load. There is no other load. It is a unique load, the unique load case, creating a parabolic moment diagram is a uniform load. So I'll jump forward to the chase. We're only going to have point loads and uniform loads in this class, and in reality that's effectively all you really have in practice too. So I can work with the last diagram and take the area under the shear diagram and get that the maximum moment is WL squared over 8. Not a big surprise with a uniform load. What we are going to do is solve that for the uniform load. That's what we're going to be interested in. This is going to be the equivalent prestressing load. So remember, we just have a tendon that's stressed inside concrete. And that primary prestress moment diagram is F times E at every location. Okay, we can use that to just go straight and calculate this moment diagram. What you're going to see is what's going to be much more powerful for us is to calculate this fictitious equivalent load and use that load as a load case to come up with this same moment diagram, this same shear diagram. We're going to try to do what we do as engineers. We like creating loads. We like working with loads. We like Camtasia must have just crap out on me every once in a while. So here we are. We like working with loads. This whole concept of being able to take the fact that a tendon group is physically within a beam and it's got an eccentricity from the concrete center of gravity, that can all get replaced, according to T.Y. Lin, by a load. Now we don't really even need to know where the tendon is within the beam, what the eccentricity is. All that stuff can fall by the wayside if we can do this whole analysis only considering this to be a load. Now, it's not really a load. That's why we keep using this magic word, equivalent load. It's going to give us equivalent results to the primary pre-stress moment diagram being derived by just taking the force times the eccentricity. But equivalently, we can get to that same answer if we use these loads that aren't really loads. So again, we're going to go through this, calculate that load. Where's my good thing? Calculate that fictitious load, that equivalent load, turn around, put it back on the beam, WL squared over 8 it, like we love doing, and come up with, that same moment that we started with. That same moment that we got by taking the force times this eccentricity. So we're getting to the same place, but we're doing it a different way. And this way is going to prove to be extremely powerful. So just like we did when we had the point load, we're going to have a tendon diagram, which everybody in the world forgets, and you'll be part of that. I hate to say it, but I've done this long enough. We are going to stop considering this. We're going to do it in your first homework assignment. You are going to create the tendon-only diagram, get that tendon by itself, a tendon group in equilibrium. You're going to turn around and do the exact equal and opposite on the concrete loading diagram. Get yourself convinced that these are equal and opposite, that are actually statically canceling each other, creating a grand total of nothing statically. But by the time I give you an exam in the 5th week and ask you about that, a number of you will have forgotten about this diagram. You will be entirely focused on this as if it's the only thing happening. And when you do that, you're going to not be statically correct. And I'll show you how that works in just a second. So end anchorages We talked about it a little bit, but when we are anchoring off the center of gravity, which we will almost effectively never do in practice, but this is a good academic exercise. This is the force on the tendon going this way. On the concrete, it's turning around and going this way. As we can see, it would go right here. We are always going to move that force up to the center of gravity of the concrete. We're going to do that because we are going to calculate stresses using this equation. If we're going to use this equation, we want this to be broken out and separate. And that's what happens when we place this force at the center of gravity of the concrete. All right, give me a second. If we place that at the center of gravity of the concrete, then we can always use this term. And that gets rid of that compressive term. Now we look at that pre-stressing moment diagram divided by the section modulus, whether or not it be the top or the bottom, depending on where we're looking. And we can separate the axial force from the flexural component. So that's why we are doing this. That's why this force will get moved up. Whenever we do that, we are creating a condition that's not statically correct. So if this force gets moved up, that is creating a fictitious moment in that direction. We have to counteract that moment in the opposite direction. We're always going to be moving that force by the eccentricity. So that equivalent moment that we're left with will always be F times Z at the end. So whatever eccentricity we moved the tendon to get it to the center of gravity, that is the eccentricity by definition. And that force multiplied by that is a primary pre-stress, is an equivalent moment. So that leaves us with cantilevers. And I really like cantilevers. I like them for many reasons. Mainly because we in post-tension concrete can do them easier than anybody else can. In wood, cantilever is a tough thing to do unless you place a beam over a post. You can cantilever it that way, but that's good for about one level. In concrete, we're cast in place. We may want to be level after level after level of doing the same thing. Wood, that would kind of fall apart in that situation. It's not easy to make wood cantilever on a regular basis vertically up a building. In steel, it usually means a lot of welding. So there's a real premium or expense in steel or wood. In cast-in-place concrete, you can certainly do this, but this will start to sag over time, a lot of times. And in pre-stressed concrete, we can actually balance that cantilever load. So we can make that straight and flat, or as straight and flat as we feel like it. So we love cantilevers in pre-stressed concrete. It gives owners and architects all kinds of freedom to do fun things and get the columns away from the edge of the building and cantilever distances out, and a lot of people like that. So let's look at the cantilever. So the moment at this location, remember, we can always just go right to it. The easy way to do this is just the moment that must exist at that joint is the force times the eccentricity. Now, the eccentricity at that location is actually A being the largest displacement, the largest offset of the tendon. Infinite number of E's, but E max is equal to A at that particular location. Now, I don't love the way I presented this, but the moment on a cantilever with a point load, well, let's back up. Let's look at the tendon diagram. The tendon is being pulled on, it's being held down, it's going to be pushed up there. So those are the equivalent loads on the tendon. The exact opposite will be placed on the concrete. So that equivalent load is going up on the concrete, going down on the concrete here. But we know that the moment is P times L. That's just basic statics. It's also equal in this case to F times A. And if I solve for the equivalent load, I get F times A over L. Now if I put that back in, obviously put that P in here times L, I get F times A. So I don't think that is a particularly complex way of looking at cantilevers. You can also, and probably the best way, is to always just take the component of this, just like you did before, and that is the way to calculate that force. Calculate that one, and then that force, once you have it, times L, is the primary pre-stress moment diagram. So you can actually approach this multiple ways. I'm probably confusing you by all the ways that I'm doing it. But the end result is you've got point loads. Those must end up equaling the force times the eccentricity at every location. A little more exciting when we put a cantilever profile on. It's the same thing. To keep this profile the way it's shown, there must be an equivalent load on this, if that's the tendon. There must be an upward load. So this is keeping the tendon in place, some uniform load. And remember, anytime you have a parabola, that's not pretty. Anytime you have a parabola, you have a constant uniform load. I kind of derived that a little earlier. Placed on the concrete is all of that in reverse. So this is what the concrete is feeling, and that's kind of our primary goal, is to get all these loads acting on the concrete, because the end game here is to figure out what the stress is in the concrete. We really know what the stress is in the tendons because we put it there. We stress those tendons. The tendon group is in tension. It's got some equivalent loads on it holding it in shape, but that's a pretty straightforward part of it, is we put the tendons in tension by stressing them. The real question is, what is that doing to the concrete? Once again, F times E or F times A, remember there's an infinite number of E's, and the maximum drape in this case will be A, so we have E will equal A right there. F times A is the moment at this location, so we know what the moment is there. There's a uniform load. We've got ourselves convinced there must be. The question is, how do we back into what that equivalent load is? Now, on a cantilever, we know we have WL squared over 2. That WL squared over 2 must equal F times A at the joint. We can calculate what the equivalent load is on a cantilever with a parabolic profile, and this will likely come up at some point in the exam somewhere in this course. We can back calculate the equivalent load of 2 FA over L squared. Remember, there are good checks for this stuff. If you calculate an equivalent load, just put it on. Just put it on and calculate WL squared over 2 and make sure that you get F times A at that location. There are checks and balances in doing this, and that is, again, ultimately the end game. We were coming up with an equivalent load to just give us the same answer that we could actually already draw, knowing the force times the eccentricity. So You know, don't make a math mistake somewhere and not check yourself. So, and then of course when we take this equivalent load, now it's a load. Now it's a load that's not really there, but it's a load that's going to give us the equivalent answer, and we put that load, WL square over 2 it, and we get F times A. So, voila, nothing up my sleeve. That's how cantilevers work. So we've looked at point loads, we looked at linear tendon profiles, those give point loads. Parabolic profiles will give a constant uniform load, and all of those loads are equivalent loads. They are being counteracted between the concrete and the tendon. They offset each other to create a grand total of nothing. But what's useful about them is if we place them on the concrete only, we will get an equivalent moment diagram, a primary pre-stress moment diagram, that at every location is equal to the force times the eccentricity at that location. So that was the whole point. Come up with a load that gives us what we really already could have calculated just by taking F times E at every location. Okay. I think I started this by saying that this entire lecture was based on a beam with no loads on it and weightless. But not entirely true. Up until this point, it was. That actually gets you through homework number 1. You have everything you need to know at this point to do the first homework assignment. I am moving on to what I'm going to focus on in the second homework assignment. And that is, now we're going to start applying actual loads. This is the part, I hope I can say this well. I've had years and years of practice, and I'm never really truly happy with what I say. Our ultimate objective of the first half of the course is to calculate what the stress is in the concrete. Now, up until this point, I have shown you that we will have stresses in the concrete due to the fact that we just pre-stress the beam. Just pre-stressing alone will create some of those stresses. Compressive stresses, flexural stresses that give you compression on one side of the beam, tension on the other side of the beam, but that's just due to pre-stressing, and no reactions were created by doing that because there was no applied load. Here's where it gets confusing. Now we are going to apply a load. This is a real load. This is not an equivalent load. This is the load that you're used to, that you've seen, throughout your whole career in school. These are applied loads. Applied loads will have reactions, will have shear diagrams. They're statically correct. They must be. There must be a static reaction here if we're putting on an applied load. There must be a static reaction here when we put on that load. Therefore, there must be a shear diagram, a static shear diagram, statically correct moment. Applied loads will create real static reaction shears and moments. They will also create stresses. So the trick that we are doing is we are trying to figure out the stresses due to pre-stressing, which don't create any static reaction shears and moments. And then we're going to figure out what stresses are caused by the applied loads that do create static reaction shears and moments. This is where the confusion lies, because it's the combination of both of those things that create the stresses that we must check against the ACI building code. Some of those will have been due to equivalent loads. Some of those will have been due to applied loads. The equivalent loads don't create any of the static effects. The applied loads create all of the static effects. And on your first exam, I promise you, I will give you questions that make you have to really think about that. Both of them are creating stresses. One of them's involved with statics. Now, remember that the pre-stressing part of it, the pre-stressing only part, had a tendon diagram and a concrete diagram. When those summed, they canceled each other out. So all you were ever really left with is applied loads for reactions, shears, and moments. So you'll learn later that you can go through the process of putting all the equivalent loads on. They will all cancel each other if you do it correctly, and all you'll ever be left with statically is the applied load. Now, on exams, I would strongly suggest that you just simply remember that the equivalent loads all cancel each other and not waste your time, your valuable test-taking time, by putting those on and just watching them cancel each other. You will have done that in your first homework assignment, and that's the lesson you're supposed to take from there. Okay, now we're on to what you're going to do in homework number 2. And hopefully I've set the stage that we will have equivalent loads. That tendon force will be pushing on the concrete. This actual applied load is also pushing on the concrete in the opposite direction. As far as the concrete is concerned, that equivalent load is as real as any other load, but it's not. You know better. Concrete's not as smart as you are. Concrete thinks it's a load happening to it. Concrete doesn't think in terms of the fact that it itself is pushing back on the tendons and canceling out that load. It just thinks something's inside it pushing up on it. So here's the example beam, and this one's going to be straightforward because the applied load and the equivalent load are happening at the same location. Of course, in your second homework assignment, I'm not going to make life that easy for you. So without walking you through everything about the area, section modulus to the top, section modulus to the bottom, it's a rectangular section, so section modulus to the top and to the bottom are the same. Y top equals Y bottom. That's the center of gravity. Distance to the center of gravity of the concrete. So you did that in homework number 1. So we are trying to find the maximum stress at top and bottom of the beam, and we're going to use 2 methods. First, what I call the mathematical method. It's the way it was done back in the day, back before T.Y. Lin came up with the equivalent load method. And believe it or not, it was the way I learned it because, and I will never understand this, at both Cal Poly and at Berkeley, they believed that this was a superior method, that the equivalent load method had seen its time. It was something that that we did when we didn't have computers or didn't have spreadsheets, and we were going to revert back to this mathematical method. Nothing could have been farther from the truth. The equivalent load method is the dominant method. It's the dominant method in today. It's the dominant method in all software that's being written, or that has been written. Okay, let's look at this same beam. Remember the beam that we have. You guys have the notes. So I take a section cut right here at 20 feet. I know the force in the tendon because I put it there, 120 kips, and I know where it exists. This M total load is the moment created by the applied load. So it's 7.5 kips times 20 feet. So I've got the applied load moment, and what I'm going to do is take, as I told you before, I'm going to take that compressive force is actually acting right here. We're going to move it up to the center of gravity of the concrete for the reasons I explained, the negative F over A plus or minus M over S that we're going to want to break everything into. You should have, by the way, seen that in slender columns and column designs themselves, slender walls. That concept should have come up in other areas. If it didn't, that's fine. But so I'm fictitiously moving that up to here by the eccentricity. So I am going to counteract what I've done. I was statically incorrect by moving that axial load, but But I'm statically correct if I offset it and put in a moment going this way. Remember, moving this force from here up to here was creating a moment going that way. So the offsetting moment is going the opposite direction. So here's all the forces and locations that I'm considering. The stress on the bottom of the beam always will be negative F over A. You can always start with that all season long here. Bottom stress is going to be tension. So think about how the applied load has got the moment diagram creates tension on the bottom if you draw the tension side moment diagram. So positive total load moment divided by the section modulus to the bottom. And then we're going to subtract the prestressing moment, because the prestressing moment is actually creating tension at the top. The fact that the tendons are down at this location, that if you want to think it, we're not doing the equivalent load method, but think of the tendons being stressed. That is creating tension on the top and compression on the bottom. So that's our equation to calculate the stress. Minus F over A is the 120 kips. The area of the beam was 480 square inches. We had 150 foot kips of applied load moment. That's the static moment. Since this is the concrete only, we're subtracting that primary prestress moment, which was not part of the statics, but it's part of what creates the stress and part of what creates the confusion. Divided by the section modulus on the bottom, and we get that at the bottom, the stress at the bottom of the beam at 20 feet is actually 50 psi in compression. So you might be asking yourself, hey, I wasn't expecting compression in the beam. Let's back up. I've got a beam that's got a point load on it. I'm trying to calculate what the stress is at the bottom of the beam, and I think I'm going to get tension. And what did I get? I actually got compression. Not at all unusual in pre-stressed concrete. I will say, look at a location, tell me what the tension is at that location. You may actually come up with compression. So let's look at what the top of the beam, the bottom of the beam's in compression, the top's probably really going to be in compression. Again, the stress at the top, always minus F over A. The applied load, total load moment, creates compression at the top. Remember, it created tension at the bottom. The M over SB at the bottom created tension. Moment divided by the applied load moment divided by the section modulus to the top is creating compression at the top. The pre-stressing is actually creating tension at the top. So you may have to study that for a second. The pre-stressing is counteracting and should always be, if we're doing this correctly, give you the opposite of whatever the applied load or total load moment is. So we have the same negative 120 over 480 in terms of stress, which is 250 psi, 0.25 ksi. The difference, the applied load moment is creating 150 foot kips, tension on the bottom, compression on the top. The 110 is creating tension on the top or compression on the bottom. Since we're looking at the stress on the bottom, these are the signs. And it turns out that at the top of the beam, we have 450 psi or 0.45 ksi in compression. So with that 15 kip point load, Both the top and the bottom of the beam are in compression. The top was in more compression. So that's what prestressing is doing for us. We can actually create a beam. We can actually create compression throughout the entire system if we choose to do so. Now that wasn't too difficult. What you're going to find out, I hope I'm not making you dizzy, but when this condition occurs, I know that the maximum activity is happening at 20 feet. So life got a little bit kind of easy in this particular case. But let's look at what we would have done if we were using the equivalent load method. If I just go and look at the tendon, this is the equivalent load acting on the tendon. This dashed one is the equivalent load acting on the concrete. I decided to draw it this way, so a heavy reminder that these are all canceling each other statically. But I can calculate, again, that this tendon was going up 11 inches over 240 inches. It was doing the same thing on both sides. If you remember, that created 11 kips of equivalent load. Now remember, I've taken the tendon out now. There is no tendon. We took this tendon that was doing this. Tendon was doing that. We took it out. Now we don't know or care where the tendon is. This concept of eccentricities throughout the beam is now irrelevant. We're not doing that in the equivalent load method. In the equivalent load method, we calculated that there is an equivalent load on the concrete going up of 11 kips. Now there's also an equivalent load on the tendon group going down 11 kips, but we're not considering that. We've separated the material only, or the concrete, it's going to be concrete real soon, from the tendon group. And now we're just going to focus on the concrete. But don't ever forget that tendon diagram is still there. It will still superimpose onto this and wipe that out. But it's very convenient for us, if we're just looking at the stresses in the material, to look at what's happening just to the material, just to the concrete. And if we're just doing that, concrete thinks there's 11 kips pushing up, 15 kips coming down, and a net effect of 4 kips, the difference between those two. So I can analyze this beam. This is what T.Y. Lin said. Analyze this beam as if only 4 kips are on it. With the 120 kip applied compressive load, and these won't come into play in the moment diagram, but they're there. So PL over 4 with this 4 kip point load is 40 foot kips. Now I can just approach this as I would any other material with loads on it and just say, I'm interested in the stress at the bottom. I'll look at M over S, section modulus on the bottom, minus F over A. All I care now is that I've got a net 40 foot kips of load, and that net 40 foot kips of load creates tension on the bottom. I've drawn this moment diagram to the tension side. So I know tension's on the bottom, it's below this line. Minus F over A. And lo and behold, I get exactly the same answer. I get that same 50 psi in compression at the bottom of the beam. Do the same thing, minus M over S, because now I'm looking at the top. This moment diagram said I was creating tension on the bottom. I must be creating compression on the top. It has to be that way. So this is a negative M over S to the top. It's creating compression at the top. The F over A is always creating compression, so I've got a negative there. That minus 40 foot kips times 12 to get some inches in there, divided by the section modulus to the top, minus F over A, and again, I get exactly the same answer. So two different methods of approaching this. One, we had to care about where the tendon was. It mattered. It mattered what the eccentricity was, where this tension force was occurring. I had to offset it by an eccentricity, come up with a primary pre-stress moment. In the second method, the equivalent load method, I didn't care or know or care where the tendon was. That became an irrelevant thing. We took the tendon out and replaced it with a load on the concrete, and we got the same answers. I will promise you this will become by far your favorite way, the best way to calculate stresses in beams. This will turn out to work when the loading is complicated, when the tendons aren't exactly balancing the applied loads at the same locations. In fact, that's what your second homework assignment's about. It will work in multi-span situations, which is the most powerful thing. We're going to fairly quickly get past these simply supported beams that don't exist in actual practice. We're going to go to multi-span systems. This will work just as easily as it did here. Whereas trying to follow that tendon and force times eccentricity through an indeterminate system will prove to be effectively impossible. That's what T.Y. Lim was doing for us. He was fixing, I guess, fixing a problem. That problem was that while it was analytically possible to design pre-stressed concrete, it was realistically impossible. Once he showed us that we can take the tendons out and put loads in their place and analyze the system and get the same answers, then pre-stressed concrete became available to everybody. Now, I do want to walk through the statics of this because statics are best friend, and I want to show you this is what we just did minus that 15 kip load. This is missing this. This is just looking at the pre-stressing. So everything we just went through minus that applied load. So we're just talking about the pre-stressing. On the concrete, we have F over A, 250 PSI, and at 20 feet from the left, we had M over S, a moment of 0.55 KSI. Now that was F times E. I've jumped a little bit. 120 kips times 11 inches, 1320 inch kips. M over S, hopefully you'll buy into it. The difference is we don't have the applied load that we had a minute ago. So just due to pre-stressing, we have 550 PSI, 0.55 KSI top and bottom. So we have that here, and we have that here. So that stress was generated by a force of 120 kips. So I can take this stress triangle, 1/2 the 16-inch width times the 15-inch of depth of the beam times that 0.55 and get a force of 66 kips. That must also be the compressive force. Remember, just due to pre-stressing, we have tension on the top. That's why this is on the right side of this line, and this is on the left side, compression. And 66 kips TC couple to create that moment. Those add up to this. And we don't have equilibrium. The 66 kips cancel each other, but we're left with a net 120 kips. So if you're only looking at the concrete, it looks like it's not in equilibrium. And that's where confusion lies with a lot of people. It appears that we're doing something that's not statically correct. And that's where people get confused. It's because they completely forgot about the other diagram. And most of the world, when you go out and live in it, will have completely forgotten about the tendon diagram that you did in homework number 1. When I take that 120 kips and superimpose it with all of these forces, I get this. Now, this plus this, what's happening in the concrete plus what's happening in the steel, gives me these forces at these locations. And you can spend a little bit of time with this if you want. Now all of a sudden statics is back to what we like. It's back to working. But you can't look at the concrete only or the steel only and get statics. You can't separate the two. They need each other. They are working together. To get the full picture of the beam, you've got to look at what's happening in the concrete plus what's happening in the steel to get the statically correct answer. But this, and this is where it gets confusing, and I'll try to spend as much time with it as I need. This was all we needed to calculate the stress in the system. We only needed to look at what was happening to the concrete because we're only interested in the stress in the concrete. So we put all the forces that the concrete thinks is happening to it, and we ended up getting the right answer. We're about to do a more complicated problem in the next lecture, and you'll see that. But it's not statically correct. It gives us the right stress answer. But remember, we were working with some of the stresses that were created by prestressing that didn't create any statics. And then we were dealing with a force that was entirely due to statics, creating stresses also. We combined those. But not until we throw all of everything back in the pool do we get statics in the section. So, okay, we're going to stop now. I want you to think about that. And the next lecture we're going to move on is something that hopefully completely shows you definitively why the equivalent load method is the superior and really only method that we can use soon as things get even slightly complicated.